could do things with.
They were clinging to the old paradigm when Mandelbrot and a few people were way out there bringing in the new paradigm. And he used to call me up on the telephone late at night because he was bothered, and we'd talk about it. Mandelbrot was saying, this is a branch of geometry just like Euclid. It offended them. They said, no, this is an artifact of your stupid computing machine.
I know very well that there is this line that fractals are pretty pictures but are pretty useless. Well, it's a pretty jingle, but it's completely ridiculous.
Mandelbrot replied to his critics with his new book, The Fractal Geometry of Nature. It was filled with examples of how his ideas could be useful to science. Mandelbrot argued that with fractals, he could precisely measure natural shapes and make calculations that could be applied to all kinds of formations, from the drainage patterns of rivers to the movements of clouds.
So this domain of growing living systems, which I, along with most other mathematicians, had always regarded as pretty well off limits for mathematics and certainly off limits for geometry, suddenly was center stage. It was Mandelbrot's book that convinced us that this wasn't just artwork. This was new science in the making. This was a completely new way of looking at the world in which we live that allowed us not just to look at it, not just to measure it, but to do mathematics and thereby understand it in a deeper way than we had before.
As someone who's been working with fractals for 20 years, I'm not going to tell you fractals are cool. I'm going to tell you fractals are useful. And that's what's important to me.
In the 1990s, a Boston radio astronomer named Nathan Cohen used fractal mathematics to make a technological breakthrough in electronic communication. Cohen had a hobby. He was a ham radio operator, but his landlord had a rule against rigging antennas on the building.
I was at an astronomy conference in Hungary, and Dr. Mandelbrot was giving a talk about the large-scale structure of the universe and reporting how using fractals was a very good way of understanding that kind of structure, which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helge von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable in my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well. And I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was, frankly, an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals, experimentally, I came up with a very wideband antenna. And then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have self-similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas sticking out at the same time. The alternative option is you can let your cell phone look like a porcupine, but most people don't want to carry around a porcupine.
Today, fractal antennas are used in tens of millions of cell phones and other wireless communication devices all over the world.
we're going to see over the next 10 to 15 to 20 years that you're going to have to use fractals because it's the only way to get cheaper cost and smaller size for all the complex telecommunication needs we're having.
Once you realize that a shrewd engineer would use fractals in many, many contexts, you better understand why nature, which is shrewder, uses them in its ways.
They're all over in biology. They're solutions that natural selection has come up with over and over and over and over again.
One powerful example, the rhythms of the heart. Something that Boston cardiologist Ari Goldberger has been studying his entire professional life.
The notion of sort of the human body as a machine goes back through the tradition of Newton and the machine-like universe. So somehow we're machines, we're mechanisms. The heartbeat is this timekeeper. Galileo was reported to have used his pulse to time the swinging of a pendular motion. So that all fit in with the idea that the normal heartbeat is like a metronome.
But when Goldberger and his colleagues analyzed data from thousands of people, they found the old theory was wrong.
This is where I showed the heartbeat time series of a healthy subject. And as you can see, the heartbeat is not constant over time. It fluctuates, and it fluctuates a lot. For example, in this case, it fluctuates between 60 beats per minute and 120 beats per minute.
The patterns looked familiar to Goldberger, who happened to have read Benoit Mandelbrot's book.
When you actually plotted out the intervals between heartbeats, what you saw was very close to the rough edges of the mountain ranges that were in Mandelbrot's book. You blow them up, expand them, you actually see that there are more of these wrinkles upon wrinkles. The healthy heartbeat, it turned out, had this fractal architecture. People said, this isn't cardiology, we do cardiology if you want to get funded. But it turns out it is cardiology.
Goldberger found that the healthy heartbeat has a distinctive fractal pattern, a signature that one day may help cardiologists spot heart problems sooner.
Please look around the screen for me. All right, Cooper, we're going to do the calibration.
At the University of Oregon, Richard Taylor is using fractals to reveal the secrets of another part of the body, the eye.
What we want to do is see what is that eye doing that allows it to absorb so much visual information. And so that's what led us into the eye trajectories. Under the monitor is a little infrared camera which will actually monitor where the eye is looking, and it actually records that data. And so what we get out is a trajectory of where the eye has been looking.
Well, it's interesting how they go around the pattern.
And so the computer will get out this graph, and it will look, have all of these various little structure in it. And it's that pattern that we zoom in, we tell the computer to zoom in on and see the fractal dimension.
The tests show that the eye does not always look at things in an orderly or smooth way. If we could understand more about how the eye takes in information, we could do a better job of designing the things that we really need to see.
A traffic light, you're looking at the traffic light, you've got traffic, you've got pedestrians. Your eye is looking all over the place, trying to assess all of this information. People design aircraft cockpits, rows of dials and things like that. If your eye is darting around based on a fractal geometry, though, maybe that's not the best way. Maybe you don't want these things in a simple row. We're trying to work out the natural way that the eye wants to absorb the information. Is it going to be similar to a lot of these other subconscious processes? Body motion. When you're balancing, what are you actually doing there? It's something subconscious and it works, and you're stringing together big sways and small sways and smaller sways. Could those all be connected together to actually be doing a fractal pattern there? More and more physiological processes have been found to be fractal.
Not everyone in science is convinced of fractal geometry's potential for delivering new knowledge. Skeptics argue that it's done little to advance mathematical theory.